what I'm going to talk about is the way that we constructed in the UK a program to start to exploit quantum physics of an unusual kind. So I'm going to run through that background of what we're able to do. And I'm going to pick up some examples from the UK program. I'll do a little bit about what's going on around the world as well. Okay, so let's see what we have to say about quantum physics and different things to do. Oh, it really is response to structure of matter, obviously. It also allows transistors and lasers to work, and they've been transformational. I'm going to call that quantum 1.0, by the way. And you can see why as we progress, because I'm going to introduce 2.0 in a moment. It helps to sell slightly daffy new age books and television programs and so on. So that's certainly the kind of thing that the general public often, if they know anything about quantum, will have picked up. And whenever I give a talk about quantum, if they've been reading the newspapers or magazines, they think I'm going to talk about quantum computing. And I'm not just quantum computing. I'm going to talk about a raft of things. And I hope you can see this kind of funnel of things that we developed, where we have some very long-term goals. That is to work out ways in which quantum physics can be transformational in computing. It's a kind of long journey. And that means that we need to better control atomic matter or photons with exquisite precision. It's a long journey. To that longer-term goal, there are things that we pick up en route that have immediate applications that are going to be transformational. So in particular, I'm going to talk about clocks and timing, communications and sensing, ways in which you use the quantum bits that I'm going to be discussing with that long-term aspiration, but not forgetting that there's a whole raft of things that are going to be influential. Now, I've got a little note to myself here to say what I mean by the power of 2 to the n. Now, what on earth does that mean? Okay, so let's have a look. If I want to build a register of bits, classical bits, things that sit in your computer, classical bits can have in binary, they can have a value of 0 or 1. So if I want to build a 3-bit register, rather feeble, but a 3-bit register, I can have it in 8 states, 0, 0, 0, right through to 1, 1, 1. Well, can I do that in quantum physics? In quantum physics, you can make something that represents a binary bit with a value of 0 and 1. But better than that, you can put it into a superposition of 0 and 1 at the same time. This is one of the unusual characteristics of quantum physics, that you have an amplitude for being in those states at the same time. So let's build a quantum register, a 3-bit simple one. Well, we've got those 8 states. So I can put the quantum register into a superposition of all of those 8 states together, 0, 0, 0, right through to 1, 1, 1. Now, let's imagine that I've got n of these bits. That will allow me, if I can put them into this superposition, 2 to the n states. So that exponentiation of the size of the state space is extraordinarily important. Imagine if I could put 1,000 bits into superposition and control them. 1,000 bits is not really terribly large for a classical computational machine, but 2 to the 1,000 is larger than the number of particles in the visible universe. So the state space for 1,000 quantum bits under control is larger than the largest possible machine that you can imagine classically. That's the challenge. Right, let's see how we go. So what we've been doing over the past several years in the UK is building a kind of quantum alliance. And it's enabled us to build a 1 billion quantum technology program in the UK. that I've been involved in helping to set up and to steer and to extend. And to do this, we needed to build a quantum alliance, engaged activity, coherently planned between academia, government, and industry. Academia, because that's where scientific knowledge and future breakthroughs come from. Government, because they can be a customer, early adopter, and of course, a paymaster for some of it. In this, building that quantum alliance was not easy. So what we did is we built a common board of stakeholders. Stakeholders indicated at the bottom of this slide. Bose, the government department, is our leading government department that funds this. The industrial strategy also. I'm gonna try and get out of my video just in case it stabilizes things better. Okay, government departments, Bose, industrial strategy as part of the Industrial Strategy Challenge Fund. The lead research council initially was EPSRC, but now we've also got STFC involved, the Knowledge Transfer Network, the Ministry of Defense, DSTL, the Defense Scientific and Technology Laboratories, the National Physical Laboratory, and the National Cybersecurity Center, a part of GCHQ. Now, what are we going to be talking about here? What's this 2.0 that I mentioned at the beginning? Now, quantum technologies actually exploit optical or electronic devices in two ways. We use superpositions, this ability to be in two states at the same time that I just mentioned. Those superpositions are incredibly sensitive to the environment. They fall apart. Instead of being in two states at the same time, you're in either one or the other state. It's quantum, but what we can say, well, look, if it's really sensitive, that's what you need in a quantum sensor. Also, the superpositions contain more information than the components do, and they can be used in communication in interesting ways. The other part of what we're doing is entanglement, exploiting the strong correlation between two separate entities. And entangled states are kind of interesting states. They're impossible to copy. That may well have implications when we do build a quantum computer, in that if it's not possible to copy, you can't do a backup. Equally, you can't measure it without destroying it. And that's integral to what we're trying to do with our new quantum communication strategy. Okay, so let's see why quantum in the UK. Why did we start to build this rather large initiative? Well, certainly there's an exceptionally strong science base throughout the country. Quantum science has always been highlighted in various international reviews of the strength of the subject in the UK. Government departments, agencies, industry and academia working together in really a collegiate and cooperative way is an unusual strength of the UK. That's enabled the UK government to commit over £1 billion of new money over a decade for this transformative technology. It is really the largest amount of resource in a disruptive technology that's ever been committed by the UK government. Underpinning this is an incredibly vibrant part of the UK economy. Part of that is the UK Photonics Industry, and I bet most of you would never have heard of it. The UK Photonics Industry contributes slightly more to the GDP of the UK than pharmaceuticals. It's not widely known. It's really part of the supply chain process. It sits in 1,600 companies, but it grows at more than 8% per annum, and over 75% of its product is exported. It really is a gem of the UK technological industry. So the key performance indicators are really there. The National Quantum Technology Programme that I look after is widely admired worldwide. Let's see why. Let's see what we do. 21st century technology has been built on things that have really been accelerating over the past 3 decades. Since the 1990s, we've really been able to understand a great deal more about some of the fundamental nature of these quantum correlations of coherence and entanglement. And we believe this will have similar societal impacts to that first quantum revolution that we spoke of. So the subtle quantum physics, it really took quite a long time in the 1980s, 1990s, and the beginning of this century to actually understand all of this. Certainly the groups at Imperial College played a major role in this. We started to work out what the exploitation paths of this science could be towards the end of the 1990s. By starting this UK program, way in advance of other countries, we believe that we have about a 5-year lead on time to technology insertion in a number of areas that I'm going to speak of. And there are some game changers. They have defense and security implications as well as civil implications. They generate sensors with unprecedented sensitivity, new modalities and capabilities. We can start to look at secure communications. And I've already indicated the revolution in computing capability. So how did it start? By a lot of heavy lifting of convincing government that this was really an important area. And in the spending review, the autumn statement in 2013, the then Chancellor of the Exchequer committed what was then 270 million of new money to build on this great science base to create new opportunities for UK wealth creation. So it was always the intention to look at ways which we develop this science and develop new and emerging technologies. We focused on 4 key areas: quantum sensors and metrology, quantum imaging, quantum secure communication, and quantum computing and simulation. So that initial investment, as I said, it started with the autumn statement. 2014 is when we started to put money through the door. What did we do? Well, here's some of the successes for this the first 5 years of that phase. Well, firstly, that 270 million grew to just under 500 million by commitments from other places. We trained 150 students through our centers for doctoral training, fellowships, PhD programs. The projects were funded by the Ministry of Defence through DSDL, right from the very beginning, where they said, it's up to you. Hire the best people you can. Their training or funding in part from the National Physical Laboratory. We have over 25 quite vibrant startups. Looking at business engagement, over 100 engagements in Warren Strategy Challenge Fund. We started at the very beginning in phase 1 with 20 million of industrial strategy money to demonstrate an appetite. What did we end up with? We ended up with 30 universities working together, over 150 partners from industry working together, a lot of great science, but already some demonstrators of new technologies. So by 2016, we started to look at ways in which this quantum technology development will give us a place to start to accelerate what was going on in the UK. And within the Government Office of Science, Mark Walpert and I produced this review, the Blackett Review. All of these reviews are called Blackett's after Patrick Blackett from Imperial College, one of the great pioneers of so we'll a survey with a lot of people in to provide recommendations to push the quantum technology program forward. We both appeared at the select committee. We got a considerable endorsement by the House of Commons Select Committee. That enabled us to start building the second 5-year phase. We produced a strategic intent document. It was actually finally published in November 2020. We highlighted various things we were doing. But as I said, the overarching aim was to create a quantum-enabled economy. And that strategic intent document has a number of case studies that I think people might find of interest about what we've achieved and what we want to be able to do. But the 4 strategic objectives on the right-hand side, to stimulate growth, innovation, to maintain our excellence in research and technology, research has to go hand in glove with this, because otherwise you starve the pipeline, and to grow and attract and retain talent. So where are we now in this pie chart of investments? As I said, the 270 million that we started to put out in 2014 grew to a great deal by the end of that first year phase in 2019. What did we do? Well, firstly, in that first phase, we started with 4 hubs, coordinating centers for the key areas that I spoke of in terms of imaging, communication, computing, and sensing. We renewed those hubs. I'm very pleased to say Imperial is now fully engaged with those research hub activities. We persuaded government that we needed to invest in a national quantum computing center, which I shall explain towards the end of the talk. In order to provide the right sort of test, measurement, and evaluation for this program, we also invested substantially at the National Physical Laboratory to build a thing called the Quantum Metrology Institute. I'm the chair of the QMI. The others, that 8% in that pie chart, represent other government departments that have started to invest. But you can see from this pie chart, the biggest single component of all of this is our industry engagement. Rather strangely, through a lot of negotiations, we managed to generate a government commitment to the Industrial Strategy Challenge Fund with a convincing case as to where industry would also put their matching funds. So we have a skills package, National Quantum Computing Center. We've started to look at international engagement. We have a CubeSat experiment with Singapore on communication via satellite. We've got some innovation programs with Canada, and we're looking at ways in which we engage with Australia. So that's where we are now in terms of the pie chart. It really is very substantial. So here is the focus of what we're trying to do. On the left-hand side, all the various things that we're trying to realize: compact atomic clocks, and I explain why they're necessary for a number of things, time stamping and so on. Sensors and metrology, where quantum effects are being exploited, secure comms, simulators, and computation. And within our challenge fund, the pie chart on the right-hand side demonstrates where we put all these various pieces. Interesting growth in an area called components, where we're feeding the supply chain for the various parts that make up the communication, sensing, timing, and computing realizations. Okay, so we currently have 30 universities and 100 companies signed up and spending their own money in these programs. Right, so back in 2015, I got McKinsey to look at what was going on in terms of the annual spend in quantum technology around the world. These are in, for reasons that escape me, in hundreds of millions of euros. Okay. Sorry, in millions of euros. Okay. And this is the non-classified part. It's very hard to work out what's going on in the quieter world. And you can see that the United States, 360 million per annum was being spent on quantum technologies. In Britain, 105, Germany, 120, China, 220, and so on. Okay, so lots of players in this space already by 2015. Where are we now? Best estimates. Where we are now is a massive investment in the United States and a stupendous investment in China, where they have very long-term planning on commitment to quantum. Okay, right, so let's look at some of the enabling science, in particular, some of the parts that Imperial has played quite a substantial role in. a lot of what we're able to do is to manipulate atoms at the quantum level. One way of doing that is to cool them down. And you can cool atoms down by throwing light at them. It's a bit like stopping a bus by throwing snowballs at it. If you have enough snowballs, you'll do it. So if I throw millions of light particles, photons at an atom, it will slow it down to incredibly low temperatures. Once it's at very low temperatures, the velocity, of course, is therefore much reduced. And you can hold and control them for longer, and therefore you can be more precise in what you do. So I take laser cooling, I make cold atoms, I continue to cool them, and eventually what happens is that they're so cold that this quantum mechanical wave-like property starts to dominate. So instead of looking like particles, they look much more like waves. And as we continue this cooling, these waves condense into what's called a Bose condensate. The atoms themselves behave like light waves coherently. And what we end up with is a matter wave. It's a bit like a coherent laser beam. And just like laser beams, you can interfere them. If you can interfere them, you can build interferometers. If you can build interferometers, you can start measuring things with them. And so by putting them onto a chip, for example, you can measure rotation, gravity, and acceleration. In every one of those, Imperial has played a major role. Imperial is a major force in cold atom science, in quantum optics, and quantum information science. Right, so that's one of our vehicles in terms of enabling it. So what are we going to do with it? So let me focus first on quantum sensors, on timing, and on imaging. So we're going to build new time standards, in particular chip-scale atomic clocks. And part of that is because we are seriously vulnerable to an over-reliance on GPS. And I'll explain that later on. So building clocks that give us a holdover is going to be quite important. And it'll enable us to build what's called a Quantum Navigator, which I shall explain in a moment, how you navigate without GPS. We can build these things on chips for accelerometry, for gyros, gravimetry, magnetometry. You can build systems that will image through walls and around corners, as I'm going to explain. You can use them to sense gravity, and that's useful for oil, gas, mineral extraction, and also, of course, defense. You can build electromagnetic field sensors of exquisite sensitivity. So this rather peculiar picture on the right-hand side in the middle is a thing that's not very different from a cycle helmet, and it's monitoring brain activity. It's non-invasive, and it works by having little processing atomic spins that we're measuring that's sensing the electromagnetic behavior in the brain. That's being led by the group at the University of Nottingham. And that group has already built prototypes that are being rolled out for testing for looking at epilepsy diagnostics in hospitals in London. So improved sensors for health, brain imaging, heart imaging. I'm also going to show you some novel cameras with single photon detection that allow us to make, I started to use this phrase, making the invisible visible. And I'll show you how we can see without being seen. Okay, so some examples. Clocks. Why are we worried about clocks? Now, before lockdown, I used to say every one of you has used this today in your sat nav, but with lockdown, but is enabled these superpositions. It's how an atomic clock works. And what we've done is put atomic clocks into satellites by geodesy, by looking at the timing between the signal from each of these satellites. We can work out where you are. Okay. And it's used all around the economy for all sorts of things, way beyond its initial intent. So we did a completely separate Blackett review on the vulnerabilities of these GPS-like or GNSS satellite navigation systems vulnerabilities. And I'm in the middle of doing some fairly complex work for the Cabinet Office on exactly this, about what we need to do to understand the resilience of the UK system. Okay, so the march of time. How do we build clocks? Let's look at the fraction accuracy. This is a double log plot, by the way. There we go. So right at the very beginning, sundials, not terribly accurate. Pendulum clocks, reasonably accurate. Quartz clocks, fantastically accurate. Then we started to use these atoms in superposition. And so what we have is a thing called a cesium fountain clock. And there aren't very many of those, but they define the second for us. There's one sitting in Teddington at NPL, and they contribute to the definition of the second. What we also have are, moving away from the radio frequency or microwave clocks, we've got the possibility of building optical clocks. Optical clocks are even more accurate, and over the next few years, we're going to have to redefine the second in terms of those optical clocks. So a tremendous march of accuracy in those kind of atomic clocks. Okay. So as well as these big, chunky, fundamental clocks, we can build little chip scale ones. Why would we want to? And this is one of the reasons why we were able to persuade government, or I was able to persuade government, that we really ought to be looking at investing in this area. And it's not what you would have expected. One of the triggers for getting government to worry about this was the flash crash. The flash crash, what happened in the flash crash is that automatic trading fed off each other, producing instability, and there was a tremendous crash in the value of stock market shares. An Accenture share dropped from something like $40 to a few cents in a few seconds. And also it generated some hysteresis, about 70 billions worth of hysteresis. And at the time, various people in government were asking a scientific committee that I sit on, how would we stop automatic trades? And we said, forget it. Automatic trades, beating latency, that's where you make more money. What we have to do is to put time stamping atomic clocks in the network so that we can work out who did what in what order right through the network, in every switch, every router, every server, every processor, so we know exactly what's going on. Okay. At the moment, we've got an awful lot of networks that are synchronized to GPS. I'm going to tell you a little bit about the worries that that generates. So the flash crash made us start to think about precisely what we needed to do to produce atomic clocks in networks for time stamping. That was the initial seed. And if you think about GPS, it's not just your sat nav. It supports power grids, the distribution of power around the country. It supports our banking operations. If GPS goes down, so does your ATM. It supports transportation, obviously. Also communication systems, because an awful lot of the packet switching is enabled by GPS precision timing. So we've got this overdependence that the inventors of GPS never really ever intended. Okay, the economy depends upon it, and we've got no backup at the moment. So let me tell you about GPS jammers. What happens if I produce a malevolent signal? Now, because the satellite is broadcasting a tiny signal, your GPS receiver is seeing a tiny amount down on the ground. Such a tiny amount that if I have a jammer, I can completely disrupt everything. Okay, large-scale jamming is happening all around the world. Serious organized crime is using it. We know that it's being used in conflict zones like Iraq and Syria. Very large-scale jamming activity in Korea. A couple of US naval vessels 14 years ago, an experiment, they blocked GPS signals in San Diego, and it meant that harbor traffic management was disrupted. The mobile phones went down, the ATM machines went down for 3 days. and I ran it in the City of London. The picture on the right-hand side shows you what happens. You really bring down a huge amount of the ability to do all those things that I spoke of, not just navigation, but essentially a lot of critical services. Now, this picture came from our colleagues in a great company called Kronos, who experimented on this. So we're really vulnerable to this. Okay. So building clocks is really important for us to be able to provide this backup system, if you like, a flywheel, if GPS goes down. But what happens if you can't see GPS at all? And this is an example. The instrument prototype stage, and this particular thing is called the Quantum Navigator. And this is a collaboration between Imperial College and a group of Ed Hines, a company called M Squared, and of course DSTL. So building this, it's got an accelerator within the same thing using cold atoms. It's got a gyroscope, and that will give us our navigation. At the moment, it's pretty chunky, but that's what you expect in a prototype. And then size, weight, and power is then engineered later on. Okay, that's one example. Let me come back to my jammer story. I really love this one. This is my favorite villain. A truck driver in Newark, he bought a $100 GPS jammer, thing that goes into a cigar lighter, and he would plug it in and leave his truck so he could visit his girlfriend. And that way the firm that employed him didn't know where he was. Trouble is, he parked this truck by the side of Newark Airport. So planes just couldn't land. It really, really disrupted Newark Airport. That guy's in jail now. Other people, right, stealing cars, GPS jammers, all the rest of it. Now, in this country, you can actually buy a jammer. You can get one from the web. It's illegal to operate it. Be warned. But they are prevalent, and the incidence of jamming is growing. And I think everybody will experience, if they go for a reasonably long drive, their GPS will drop out for a bit, and almost certainly it will be a vehicle with a jammer going past you. Right, now, next thing I want to talk about is quantum imaging. Well, we've had laser rangefinders for many, many years. You send a pulse of light out somewhere, it gets reflected. The time taken gives you the distance. But there's something new that we can do. We can make pairs of photons. They're born together in an entangled state. They're highly correlated. One of them I'm going to use as a trigger, and the other one I'm going to send off to the target. And so these are incredibly low light intensities. And we're going to correlate the one that comes back with the one we kept. So very low light intensity gives you the ability to do things undetectable by anyone else. I'm also going to show you how we can see around corners with this. Okay. So this is my animation of what's going on in this. This is the building block of a lot of what we do. This is on an optical table where we have ultraviolet radiation coming in from the top left, high energy UV blue photons, and then on that optical mount is a crystal, and that crystal is down converting that incident blue light or UV light into two red or visible photons. That conversion efficiency through nonlinear optics is really tiny, perhaps only 1 in a billion, but we don't care. We don't need a high flux. But these photons that are emerging are really highly correlated, more correlated than you can possibly imagine. For the technical in the audience, what we're doing is building Bell pairs, highly correlated. So we've got these pairs. These are so highly correlated, the information you obtain on observing one of them, you can infer what's going on with the other. Right. And that gives you a really cute application called ghost imaging. So what we're going to do is have our UV photons coming in. There's our funny little crystal that down converts it into these twins, these pairs of photons. Okay. And what I'm interested in doing is imaging this thing over here labeled lambda. Okay. I'll illuminate it with the infrared twin that's going this way. Okay. And I'm going to have a bucket detector. It's not an imaging detector. It just detects everything. Okay. The twin of that infrared one could be in the visible. We'll hang on to that one. We'll put a delay line in so we can hang on to it for a bit. And we'll have a camera. And because this is visible light, that camera can be really efficient, whereas cameras in infrared are not. But what we'll do is we'll trigger that camera contingent on me picking up that red photon in the bucket. That enables us to build an image over here image that never saw that object over there, only the red line related as twins. We can infer what happens on the blue light. We can infer what's going on in the red. So we can build an image over here in blue light that never saw the object we're illuminating. It's called ghost imaging. It is really cute. And again, there are groups around the country doing this. My colleague Chris Phillips in physics at Imperial is demonstrating this sort of thing as well. Okay. How on earth can you see around corners with this stuff? Well, here's how you do it. Let's have a source of light at the single photon level, one photon at a time. It will bounce off an object, and that single photon, when it bounces off that object, will emit spherical waves. Spherical waves will then propagate out to this person who's in that building that you can't see. But the person will also scatter light. Spherical waves again, bounce off the floor, come back up to this camera. So by using the arrival of the reflected light, what was going on, even though the person who was scattering light is around the corner. Does it work? Well, let's see exactly how. Okay. So our hidden object was over here. The field of view, it's scattering stuff, and we pick it up in this camera. And already we've been able to do standoff detection at about 50 plus meters around the corner. Not enormously around the corner, but if you're a policeman, for example, you want to know if anybody is just around the corner with a gun, this can be quite valuable. And that's what is being rolled out for, those kinds of applications. Around corners. The same timing accuracy of seeing what's just out of immediate sight is already being investigated for use in driver assistance in really bad weather, by the way. Okay. Right. So that's seeing around corners, doing ghost imaging. What about sensing gravity? Gravity is a very peculiar thing. You can't shield it. But our cold atoms that we were speaking of earlier have the ability to acquire a phase that depends on the gravitational potential it sits in. And that means you can build an interferometer that measures gravitational differences. Okay, and what we've got is various prototypes. They're pretty big at the moment, but they're coming down to the sort of size that you might one day put in a backpack. And that tells you that you have an ability now to see what's under what's beneath your feet. That's kind of important because, of course, half the holes dug up in London are in the wrong place. We don't know where the buried pipework is. If we can improve the accuracy by a factor of 2, using this quantum interference, we could probably save an enormous amount of money by locating it. And that's one of the ambitions of the group led by our Birmingham hub. You can see it's got lots of other applications. So because you can't shield it, you also look for all sorts of things like voids. If you're doing brownfield development, for example, you don't know whether there's a mine shaft or some ancient industrial development underneath you. And building a gravity imager that maps out what's underneath this is becoming really important companies. And you see it's markets for not just civil engineering of that kind, but in oil and gas exploration. And what we're looking at is differences between the specific gravity of what's beneath us. So we take a void, obviously it's got a density of 0, water 1, rock about 2.5 or 3. But if you want to know whether a shipping container that's coming in might have something seriously heavy in it, for example, plutonium, that's got a specific gravity of nearly 20. And that will show up in this kind of gravity imaging interferometer. Okay, so lots of civil applications, but there's also a strategic one as well. So the Birmingham-led sensing activity looks at a whole raft of these things. Streetworks, where we think probably that there are cost savings of over 3 billion in removing risks. 5% of project budgets for surveying, that's an enormous. You do a major capital project, 5% of that project will be just on the surveying of where you are. Okay. A lot of utilities get damaged by contractors, they don't know where they are. There are sinkholes that occur everywhere. And of course, 30% of boreholes that are drilled are actually successful. So the exploration market is very substantial. And that's why British Petroleum is one of the people engaged in our program, along with other oil companies. Right, now, so we've indicated that these quantum correlations can do interesting and useful things. To what extent is there this quantum difference? And the pioneer of this was one of the great stars of modern physics, Richard Feynman. And Richard Feynman already in 1982 had produced a really transformative article where he pointed out that quantum systems are incredibly hard to simulate on a classical machine. It's back to this 2 to the n business I was speaking earlier. The state space just grows out of control. So Feynman had already proposed that why can't we use a quantum system to simulate another? This is already the beginnings of what led to the quantum computing avalanche of ideas. So that was 1982. In 1985, David Deutsch, then in Oxford, already came up with a prototype algorithm. This prototype algorithm, he could show, could perform calculations that would be either very hard or even impossible for a classical machine to perform. Very much toy algorithms. That was 1985. But the real revolution really started with Peter Shaw on the right-hand side. Peter, at that point, was working for Bell Labs. And in 1994, he showed that these quantum superpositions enabled you to exploit what's called quantum parallelism. Quantum parallelism could deal with what's called a Fourier transform in a very effective way. And one of the things that it could be applied to is factoring. Classically, factoring large numbers is incredibly hard. But if you had a quantum machine using Shaw's algorithm, it became easy. Okay. So who cares about factoring? Well, we all do. Okay. The hardness of factoring underpins the security of the internet. It is really dependent on a number of components, part of which is called public key infrastructure. It's often called RSA after Rivest, Shamir, and Edelman, although Clifford Cox did pioneer GCHQ several years before. So there's a very large number. There's RSA 200. And if you want to find the prime factors of RSA 200, It's really difficult. I've just shown you what they are. To know you've got it right is really easy. Multiplication is easy. Okay, so checking the answer is easy. Getting the answer is exponentially difficult. And the RSA crypto system that we all depend upon whenever we use HTTPS or anything else is dependent on the fact that we need to do polynomial work to encrypt and decrypt. It's really hard because the exponential work is involved in breaking it, in other words, in factoring it. Those numbers, the factors, are actually enables the security of the internet. But if you use Peter Shor's algorithm, instead of these things being exponentially complicated, it becomes polynomially complicated. So a thing that might take the age of the universe to factor on a really sophisticated computer machine could take place in hours on a quantum machine if you had one. So that's the challenge. A quantum computer undermines everything we do in terms of a quantum ready economy. Okay. To worry. Is this one? This is the only equation I'm going to use. And sometimes I call it the Mosca equation, after my kind of academic grandson, Michaela Mosca, who came up with this idea first. It's a very simple idea, but very troubling. How long do you want your cryptographic keys to be secure? That's your shelf life. Let's call it X. How much time will it take to retool all of our infrastructure with things that are quantum safe? Let's call it Y, the migration time. How long will it take for a large-scale quantum computer to be built? That's the collapse. The Mosca theorem is if X plus Y is greater than Z, you'd better worry. Okay. And the key point of this is that all the best expectations of putting a large-scale quantum machine of the order of 10 years, 10, 15 years. How much time will it take to retool to be quantum safe, to be quantum resistant in your encryption? That's going to be of the order of 10, 15 years. When do you start working out ways in which make the internet resilient? Well, how about last year or the year before? That's why we're also looking really hard at these kinds of threat spaces. So the timeline for the quantum computer. So if you see these kinds of things, the large-scale quantum computer, 10, 15 years away is the best estimate. 1 in 7 chance Michaela Mosca thought of a crypto primitive being effected by 2026. 1 in 2 chance by 2031. Okay, so it's real. Right, so what are we going to do about securing things? I'll come back to the computer timescale in a moment. But on secure comms, what is it we actually do when we're trying to communicate securely? So over here, I've got a sender. I'm going to call that sender Alice. And over here on the right-hand side, I've got Bob, who's a receiver. Okay? I've got a villain in the middle, who's the eavesdropper. And the way that one might want to consider secure communication is to take your unprotected data in plain text and have some sort of mathematical transformation that folds it in with a crypto key, which you keep secret. You transmit that protected data through this hostile network. Now, the eavesdropper doesn't have that key, so it can't disentangle the key and the unprotected data. But the legal recipient, Bob, has a copy of that crypto key. Okay, so you can apply the inverse of that mathematical transformation, gets out the plain text. Bob can't do it because he doesn't have the key. So the clue to this is, how can two individuals share securely a key that no one else does? And quantum physics rise to the rescue for some of this. Okay, so part of it is, can we actually produce quantum random number generators? Random number generators that are securely safe and random. You do the right entropy extraction on it, you show that your sequence is trustworthy. And if I to my single photon sources, here's my photon being emitted. I've got a beam splitter here, so some gets reflected, some gets transmitted. It's probabilistic. Its photon either is transmitted or reflected, completely probabilistically, in the way that would have worried Feynman and would have worried Einstein, lots of other people. Okay, it's intrinsically probabilistic. If I have single photon detectors over here, I can get basically a random bit string from this. And I could distribute those random bit strings somehow. Or I could start working on quantum resistant algorithms, which are classical. So I jumped there. And finally, I can start using ways in which I can start to distribute this secret key using these single photons between the legal recipient and the legal sender, immune to eavesdropping. Now, right at the very beginning, I mentioned that you can't copy entangled states. If you try to copy it, you get what's called the collapse of the wave function. Terrible things happen, and the entanglement and the correlation is destroyed. Okay, so that's the basic theory of it. The Entanglement Protocol was invented by my student Arthur Eckert back in the beginning of 1990s. How's it exploited? Okay, this is the British Telecom part contribution to our quantum communication hub. They can exchange these secret keys down at the quantum level between the British Telecom labs at Astral Park near Ipswich, through the Ipswich Exchange, down installed fibre to the Cambridge Exchange via Bury St Edmunds and over to Cambridge University. Okay, you can establish secret key distribution between them. And in doing so, you can then start to do secure video, for example, between the two. And we launched that about 18 months ago. Indeed, what you can do is to put in deliberately a tap in here, an eavesdropping, and the eavesdropper reveals itself in terms of the process. So in quantum physics, the act of measurement disturbs what you're measuring, so the eavesdropper will always reveal themselves. So this is a secure communication protocol based on the laws of quantum physics. And it may well be secure, but only if you operate it properly. Basically, eavesdroppers have got this terrible habit of finding a backdoor way into machines that are improperly controlled. Okay, right. Do you remember the machines at Bletchley Park were able to get in because a letter never got encrypted to itself? There's always a backdoor if you're not careful. Right, so we can do this along fiber, an installed fiber, but what you can also do is to do a long-range hop. You can distribute these quantum keys via a satellite. And a really quite spectacular experiment was done. Led Jianwei Pan in China to his old PhD supervisor in Vienna, where they distributed entangled pairs and established key exchange and did a secure video between Vienna and Beijing. So it's moving out of the lab. BT and various other companies are very much involved in these things. So the Chinese satellite was called the Meteor satellite. It was a tremendous accomplishment. We have, working with Singapore, a CubeSat project to look at proof of principle for these kinds of things. And there's a lot of interest in these global works. Right, let's come back to quantum computing. This ability to be in two states at once. And I've explained already that because the state space grows exponentially, this 2 to the n is such an advantage. It behaves sort of like a massively parallel computer, and it solves problems in much fewer steps. And there is a popular misconception out there. People know about Peter Shor's algorithm if they do a little bit of reading. They think perhaps there aren't many algorithms. I can recommend a thing called the Quantum Algorithm Zoo, which actually goes through a number of algorithms that have been proposed and tested using a quantum machine. Okay, so basic idea. So we've got this great opportunity. Large-scale quantum interference via entanglement is our big resource. We compute with n qubits under control. The state space grows exponentially with the number of qubits. If you have a carefully constructed algorithm, you can solve problems in much fewer time steps. And it's transformational. So we've got a roadmap for building a quantum computer in the UK. We're well positioned to deliver hardware, software, and others. We're in the middle of building a 100-qubit prototype machine at the moment. So what you see here are ion traps on the left-hand side as the vehicle for this, some chips that contain cold atoms, and of course, things that sit in dilution fridges. And it's the dilution fridges that made a lot of noise earlier. Whoops, don't want to do that. By the work of Google, and I'll come back to that. Right, so if we look at how things looked when we first started to think about quantum computing in the middle of the 1990s, there was a huge chasm between what the experimentalists were able to do, even with the best endeavors, and what the theorists were demanding as a threshold for running an algorithm. That chasm was enormous. Okay. So here's the question. How long will it take to close this performance gap of a factor of 10,000? And nobody knew at the time, but there are a lot of guesses around. Some said a few years, some said many decades, some said never. Okay, let's see. How long did it take? Okay, how long did it take? Well, 2 decades, because we're there. The theorists found better and better and more practical ways of protecting the qubits. The experimentalists got massively improved levels of control. Okay, and so now that chasm's gone. Okay, right. So what we have in the various platforms for building these qubits is a kind of quantum Moore's law. So on this, what we've got is, it's a bit technical, this is the 2-qubit gate fidelity, the ability to entangle bits that give us this power. Okay, and there's a threshold that your computation will not be stable. If you're above that threshold, you can start to repair errors. So what are the various lines? One of the lines is ion traps, where we're manipulating cold ions that are held in an electromagnetic trap, manipulated with lasers. The next line is the superconducting qubits. Think fridge. And the final line is ion traps, where we're using microwave to address by putting in field gradients. Okay, and you can see, and these things are sitting on a log plot, that basically they started to cross their threshold around here, around, let's say 2014. And it's no coincidence that from that stage onwards, the big companies started to get seriously engaged, because what we can see is a transition from the physics of the qubits to the engineering of registers. Now, I call it a quantum Moore's law because this is on a log plot, and you can see that we are following a Moore's law doubling period, which is really quite spectacular. So the capability is there. I mentioned Google. Google produced this famous advance where they showed a quantum advantage, where they could show that they built a small scale quantum machine which outperformed classical machines. They called it quantum supremacy, a phrase that was invented by John Preskill. It's got unfortunate connotations, and many people are moving away from the supremacy word for obvious reasons and calling it quantum advantage. So what they had is superconducting chips in a dilution fridge at 20 millikelvin. And they built a chip, it's called the Sycamore Chip. And initially it had 54 quantum bits that were connected together. One of them turned out to be noisy, but they had enough diagnostics that they could turn that one off. They could decouple it. So now you got 53 that are talking to each other through a very complicated array, and lots and lots and lots of very sensitive control electronics. And what they were able to do is to produce, with their 53 qubits, bit strings that are 2 to the 53, which is really quite enormous. And what they did is a random benchmarking test, which performed that task in 200 seconds. And the best estimates would take the Summit supercomputer at Oak Ridge, something like 10,000 years. IBM contested that because they built the Summit supercomputer. But anyway, they do concede the huge advantage. Okay, so this little compact machine outperforms supercomputers in this very specific task. That already was one of the major advances. The science side of this was led by John Martinez, who's now returned back to the University of California at Santa Barbara. So, what can we do? We can build these things. We can build things out around here, 50 or 100 qubits. We would like millions of qubits, of course. So there's lots to do to bridge this chasm of realization. And the way to do it is to produce something called error mitigation, quantum error correction. But people have made enormous advances over the last couple of years in that space. So where are the people doing this sort of stuff? There are lots of startups, as well as academics being involved in superconducting chips, Intel, IBM, Google, and a spin-out from IBM called Rigetti, which is actually doing really rather well and has a UK are the leaders on the superconducting side. With trapped ions that are laser manipulated, there are 3 major leads on this. There's a company run by my friend Chris Monroe in the United States called IonQ, who's made tremendous progress. The Oxford group, who have the best quality quantum bits at the moment, have got a spin-out company called Oxford Ionics. And Honeywell came out of almost nowhere. They were in dark mode for quite a while, emerged last year, 18 months ago, with their version of this. Then there are optical ways of doing this, using photons on chips that you could manufacture on silicon. And there are companies like Xanadu, principally in Canada, but with stuff in the United States. A major spin-out called PsiQuantum. PsiQuantum was created by a combination of experimentalists at Bristol and theoreticians at Imperial, from my old group, in fact. PsiQuantum have raised over 300 million for their demonstration platform. There's also a company called Orca, which is looking at photonic quantum computing platforms, again with an Imperial co-founder. in fact, the provost of Imperial now, Ian Walmsley. Okay, there's a long-term aspiration to do all this stuff in terms of silicon, to make it match with the normal sort of CMOS technology. And that's very much led by Michelle Simmons, principally at the University of New South Wales in Australia. So lots of research activity, but already some serious interest within companies to realize this. What we're in the middle of doing now is that we're building the National Quantum Computer Center. So this rather futuristic diagram on the right-hand side, this image would be our building. It won't go up for another 18 months or 2 years. And that would be our headquarters activity by which we can engage and start looking at the engineering scale up. Well, we're focusing principally on superconducting qubits and trapped ions in the 2 major scale-up labs there, but a lot of work involving industry to be co-located. A lot of what we'll do with the National Quantum Computing Center is also engagement of working with companies and other researchers. We've got a roadmap which we've now published, and in the last spending review, we managed to get 93 million to get this underway. We're in the middle of very delicate negotiations to scale that up at the moment. We are for a few more weeks on that part of it, but we do have the 93 million to do this. Okay, so what I've done is try to run through a kind of tour de table on a very wide-ranging program. I think it's very successful. It's widely admired around the world. It's being emulated around the world. The National Quantum Initiative signed off in the United States by the White House, more or less a clone of what we're trying to do. It builds on great science to reap economic benefit. It's a good model for other areas of transformative technology. And it's been a wonderful journey by which really quite fundamental physics, Bell's inequalities, correlated photons, entanglement, all of that can be transported into new capabilities which can be engineered to produce capabilities that people would want to use. So thank you very much for listening.
Well, thank you very much indeed, Peter. That's absolutely terrific. It's a great revolution which is taking place, and we look forward to some applications. Thank you very much. You would get a round of applause at this moment, but perhaps we should turn to a few questions and answers before we unmute people. One early question was from Colin Jackson, who said, how will your quantum timing chip be used to replace GPS in aviation in particular, on global scale flights, for example?
What we believe we can do in terms of anything that's navigating where there may be a vulnerability to GPS is to have a holdover which will be resilient for about 24 hours. That's the design parameter. How can we produce the kind of performance which give you a base check over 24 hours? And so that will require, for an aviation or a shipping application, not the chip scale clocks that I've been talking about that have much worse accuracy, but rather better than that. But you've got the room to do that in a ship, certainly, in most planes you can as well. So doing that, but the big application, as I mentioned earlier, is actually putting stuff in the comms networks to do timestamping. Because at the moment, we are entirely resilient on GPS, and there's no backup.
And was the government's purchase of the OneWeb satellite system a waste of time? Was having GPS back in a backup system, do you think?
You're a very wicked man, Rod. The OneWeb purchase was to enable us to get.
I'm not wicked. I'm just translating.
I had to spend a lot of time over the OneWeb situation.
I imagine.
It does not give you a replacement for GPS. It gives you the ability to do 5G distribution from space in low Earth orbits. We cannot do global navigation system distribution from low Earth orbits with the current technology we have. And OneWeb, and that's why those of you who have been following in Parliament will know that the Secretary of State had to backtrack a few days later and say that it does not produce an alternative to when we got expelled from Galileo, if that means anything to you. It is not that. And so we had to do some very fast work to say this is not a solution to the Galileo problem. It was, shall we say, very much the enthusiasm of a particular advisor to the Prime Minister who was in position at that time that enabled OneWeb to be bought.
Thank you. Thank you. Now, somebody has commented that their local water supply has been cut off due to a contractor damaging the pipe about a kilometre away down the hill, he says. We're raining like anything here, and I blame that on the slow and intermittent connection we've had. I must apologize to everybody. Most people have stayed with us during that time, but occasionally Peter did step out. I know we're recording it, but I have a suspicion that our recording will have the same blips and omissions in that as some of us were experiencing.
Right. Yep. It should have worked for me because I do have fiber to the home, but as you say, infrastructure again. Yeah.
We need it desperately as we're all going to carry on working from home, I guess. Paul Shah, besides the industry, could you give us a sense of how the quantum revolution will affect science?
Yeah.
For example, will we be able to make new discoveries about quantum mechanics itself? How will we use it to explore our world?
I think that's an exceptionally good question. One of the things you can do when you have new sensitive capabilities is to go back to see if it can measure things that were previously difficult. And one of those, in terms of using this quantum control of things, was actually the enhancement in the gravity wave detectors that we heard in a previous Friends lecture.
Yeah.
Because they now use what's called squeezed light, which has quantum correlations of the kind that I've been discussing. But better than that, some of these rather strange atom interferometer experiments have a sensitivity which might enable us to look for dark matter. And so there is a major experiment underway to use some of these atomic interferometers and build much bigger ones, not for finding holes in the ground, but to look for dark matter. Now, what we will do, and again, this is a network that's called AON, that involves Imperial College and others, is that we'll build a drop tower where these cold matter atoms will interfere all the way down a stairwell. Okay, if that one works, then we want to drop it down a really very large potash mine called the Bulby mine. And that will enable us to look for dark matter, which is really most of the universe that we don't know about. So there is always this wonderful tandem operation of great science indicating things that you can do differently, new capabilities for measuring things. Those new capabilities can be used for great science again. And we've always known that we needed to keep these things married up.
Yes, Caro mentioned that the photograph I was exploring with him, he said it's missing the equipment that squeezes light. What effect is that?
To squeeze light, I missed part of the question there. Can you repeat it?
Yes, Fiticaro mentioned that they had added equipment in the gravity wave machine to squeeze light.
Right. So I'm going to get quite technical for a moment. The way that any optical interferometer is limited by what's called the shot noise. That you have in your light signal that you've got photons. You might be detecting n of them, and that means that you've got the ability. You've got noise limitations, which is roughly of the order of the square root of n. What we want to do is to get better than that by using these quantum correlations. And what squeezed light is it's producing phase-dependent noise, which in one phase is less noisy than the vacuum.
Wow.
Less noisy than nothing at all. Okay, that's what squeezed light is.
Right. Thank you. I'm totally confused now. Now, somebody's talked about...
Yeah, so Rod, we have Tim, who's put his hand up a little while back, and
oh, right.
I'll unmute Tim, and if you'd like to go ahead and ask a question, Tim.
Yeah, so I mean, I think about the ubiquity of RSA and that type of cryptography. It runs on my phone, it solves key distribution. And I look at quantum key distribution and its fiber optic cables and satellites and things like that. It looks like the infrastructure to support that is not something I'm going to get on my phone anytime soon. And so I'm wondering, if we crack RSA using a supercomputer somewhere first, then would you expect there to be a growth in the industry of key distribution, kind of going back to the 50s and 60s, where banks would exchange, massive one-time pads to encrypt information, to send messages back and forth, and things like that? Do you think there might be almost a step back to get that same level of security again for a while?
That's always possible for a fallback to distribute one-time paths. It's extremely painful and laborious, but it could be used as a backup. There are two things that are proceeding in parallel. One is to provide new sorts of encryption, hash-based systems and so on, that might be quantum resistant to the kind of attacks that are similar to the Shor algorithm. Now, the problem with that is you're making assumptions again that something that's hard might always be hard. It's not provably secure. So there are these things called post-quantum techniques, and certainly there's a thing which NIST insists is called not a competition to roll out testable quantum secure classical encryption, and we're actually funding part of that. So that's part of what we're doing, to see if we can actually roll that out in a way that will integrate with the existing infrastructure. So that's one thing that you think probably has that right time scale. But you mentioned that will you ever be able to do key distribution with basically consumer electronics? So it's going to be tough, but there's already prototype developments at the University of Bristol, for example, by my colleague John Rarity, that have enabled key distribution between a handheld object, not so very dissimilar to a mobile phone, and an ATM. So that consumer exchange of keys is already being tested in the Bristol area. And the company that they've spin out is actually looking at these sort of capabilities. Once you have that ability to do this photon exchanging to and fro, all you need really is the kind of photon sources in your camera and in your ATM. Now, I don't know if you know, but you've got single photon sources in your smartphone at the moment, because that's how they do facial recognition. So there's a VCSEL in your phone. It will send out correlated photons back, single photons coming back. The elements may actually already be there that we can start to build on.
Okay. And sorry, I'll squeeze another question in. So with classical computing, with a lot of the algorithms that are used, we're kind of approaching the limit of what Shannon told us would be possible back in the sort of 70s, 80s, 90s, or whenever it was he wrote his brilliant masters. How are we going to have to revisit any of those assumptions with quantum computing? Is there anything? I mean, I like to think it's purely mechanical, but I'm not a quantum physicist. Is there anything there that we previously assumed was a limit in terms of being able to squeeze information into less bits and deal with, more and more noise that we might think about again?
Yeah, there is. So channel capacity, which is what Shannon spent a lot of time on, is hugely influenced by these quantum correlations. And so there are quantum channel capacity theorems that are now being applied, and the way that you would do communication compression using quantum physics is already started to change things. So the Shannon built the underpinning structure for everything, and what we're doing is using the fact that some of the information theoretic content within Shannon's work can actually be mapped across to include the quantum effects. So you still have channel capacity, but you have a quantum channel capacity now, where those correlations are built in. No one's ever going to forget Shannon. He's our hero.
Thank you. We have still got a lot of questions coming in here. If we can do 3 or 4 to 8:30,
sure.
Then we're going to. I'll ask David Southwood to thank you. And then there'll be a small break, and after that, members will get together for 15 minutes with a glass in their hand after a short break. Now, a couple of more questions. The politics of it all. Do you foresee issues arising with large corporations such as Google having access and potentially abusing such powerful technology?
Yeah.
How are we going to sort the ethics of this?
So the ethics of these new capabilities have been something that's been worrying us for a long time. And within our national program, we have a responsible innovation program that's running on this, where we do a lot of community work, picking up what the everyday person on the street really thinks we should be worrying about. So it is true that some of the surveillance techniques that could be made possible by what we've been talking about could be exceptionally worrying. Whether they're more worrying than what's already being applied with classical technology, I'm not so sure. But it's definitely something that is occupying our minds.
Right. I look forward. They have a lot of power in our world.
They certainly do have a lot of power, and they've got very large budgets. So not just Google, but Amazon Web Services, which is a major player in quantum. They've got very large wallets. And
as Holly Lodge says, what is China up to?
We know a little bit because they're very active in publishing an awful lot, but who knows what else is going on? And they do have a massive program compared with us. And their big hero in terms of the intellectual pursuit of this, Jianwei Pan, is a good friend, and he really is a genius. So they've got a wonderful science program, but they do have an exploitation program, which you hear rather less about. So that Alibaba, Tencent, and others are very rapidly investing in the field.
Thank you. And are you working, where we got Sir Peter Michael says, are there researchers working on quantum computer languages for programming at the moment? Is that another field where people are working?
Yes, there are. And so there are a number of groups within our quantum computing and simulation hub worrying about these kinds of things. Also some spin-out companies. So both the operating system type language that you would program things in is being developed. One of the fastest growing of our spin-outs is a Cambridge-based company called River Lane, which has some very exciting ideas in this particular area. So yes is the answer. Again, it's an area where the UK has some particular strengths. And one of the things I have to worry about is the acquisition of some of our best minds in this space by Amazon Web Services. I'd quite like to keep them in the UK.
Right. Katrina Triffitt has, I think, said something for many of our listeners, including me, when she says, speaking as a non-scientist, thank you very much for making this accessible. I'd like to now ask Professor David Southwood, our chair of Friends of Imperial College, to say a few words. One of your colleagues.
Righto. Well, I have to say, Peter, that was a masterclass. Absolutely wonderful. I really enjoyed it, and I'm sure the audience did. Even in the areas where one didn't quite comprehend, you made a great deal of a complex system believable and credible. I think we all are deeply grateful for that, and your communication skills really came over, I thought, very well. So I would like to offer you a vote of thanks and say thank you for that. Perhaps I at least don't have my muting on, so I can clap. So well done, Peter. Really appreciated. I've got a couple of announcements just to wrap things up. The next item is on the next meeting for just the Friends of Imperial College, and I would indicate any of you can join and subscribe. The next meeting is on the 10th of February for going behind the scenes at the Grantham Institute for Climate Change at Imperial at 6:15 in the evening. And beyond that, on the 16th of February, so actually very soon, in fact, 12 days' time, the next open meeting is actually with a speaker called David Southwood. I'll do my inaugural lecture, and it's called Thanks to Imperial. I'm sure, Peter, that you feel thanks to Imperial too. It made my career absolutely first-rate place, and I think I'm very happy to explain why in a couple of weeks' time. That'll be at 7 o'clock on the 16th of February. Otherwise, for those of you who are members, you should have had a link, and we'll have a meeting with Sir Peter, a chat, in a very short time. Otherwise, thank you all, and hope to see you on the 16th of February, if not the 10th. Okay, good night.
In a few minutes' time on the link which will have been sent to members. Thank you all very, very much for coming, and we look forward to seeing you again soon. Thank you, and thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Bless.
Thank you.
Thank you.